Welcome to lecture number 2 for our lighting class, which talks about the properties of lighting, and that corresponds to chapters 5 and 6 in the Gary Gordon book. And let's start with chapter 5 and patterns of brightness. Basically, the book outlines what it calls the 7 directions and distributions of light. Now, that, of course, simplifies it somewhat. There really aren't just 7. There are many, but I guess these are kind of the basic ones. And actually, the book even expands on them with wall washing and wall grazing. So, the idea is to really think about these different directions. Let's take a look at them. First of all, a narrow kind of point source. One which you would typically call a spotlight, that can occur up in a ceiling, and often they're adjustable, and they tend to make a little pool of light, and you can even shape that pool using controls around the aperture, things like a barn door fixture will allow you to make a square pool of light as opposed to a round one. And then you can have wider distributions of that same downlight. This happens to be a square downlight, but it produces a round blob of light on the floor due to the lamping. And do you like this? Well, my goal usually is to get even lighting all the way down the corridor. Now, in this case, it's a pretty long and boring corridor that they've already tried to break up with these kind of decorative slashes on the wall. So maybe the blobs of light aren't too distracting, just so long as they're not too uneven. Obviously, you have egress considerations. You don't want people bumping into stuff. And that those same distributions, wide and narrow, can occur either can occur in the ground or in a soffit, or within furniture. This is the MIT chapel. That some of you may have been to, that has uplighting kind of behind I'm not sure what you'd call it, a very deep wainscoting, I guess. And if I remember correctly, that uplighting is actually daylighting reflected through the pool of water around the MIT chapel. Anyway, or you can have them in any which way. I think actually this picture looks a little funny. To me, I'm not sure what they're lighting, maybe some kind of archway or whatnot, but it does look a little funny to me the way it's the uplights are inserted into the wood flooring in a very odd way. Anyway, other distributions that you're going to see, these are the one that's the omnidirectional, the one that is kind of glowing, is what you would imagine something like a chandelier would want to be. Something where it draws attention to itself. It's kind of sparkly, which is the book's chosen term. This is as opposed to using decorative fixtures. This is a similar type of fixture in the middle of a table, but this isn't nearly as sparkly. In fact, it kind of makes you wonder, how did they get light onto the fixture? There's only light in this fixture coming straight down. Probably that's a photographer adding. The last one here, up-down lighting. This is actually my old office, in fact. My desk was right, I think, on the other side of this column here, if I remember correctly. And this is a hanging light that throws some light up to the ceiling and some light down to the ground. And you can actually get any number of distributions. If I remember correctly, this threw something like 60 or 70% of the light down. The nice part about it throwing some light up is that it really makes the space feel much more light and airy. Higher ceilings. It has a kind of nice psychological effect. But it's using most of its light down, which saves energy. And here you have wall grazing, which is when the light sources are placed very close to a material to bring out the texture. And you can see here that there's a very rough texture to this wall that's quite dramatic, called out by the close location of those light sources. The exact same type of lighting can, if moved back from the wall, will produce an even wash from top to bottom. You can even see the distribution of the light. See how it's much brighter up at the top, and then it throws a lot of light down, but it really gets the light almost all the way to the top of the wall, and that is really the goal. And in fact, that is really what we try to do here, is to get the light to the very top part of the wall. Here's another method of achieving that. These are with par lamps in a track setting. And again, you can see it's a very evenly lit wall, still a little darker at the top. There are fixtures that can make it almost completely even, but this is pretty good. It's pretty light from top to bottom, and this would be great if you had paintings that changed or some signage. What you'll see in most designs is not such a simple usage. You'll see that there's a combination of things. So there might be narrow downlighting or wider downlighting, depending on, this looks like a dressing room to me. You might have lighting that is meant to just kind of light the seating area, and then you might have wall washing that shows off materials. And the wall washing can come from up above, or in this case it looks like it's actually kind of snuck in behind that mirror. And most designs are going to have any number of combinations. This one also uses wall washing, what looks like from little point light sources, but it uses another washing technique. This is washing the ceiling and creating kind of a bubble up in the ceiling, or I don't know what you'd call it, a bean-shaped blob. Anyway, and then there's a million other things. There's cabinet lighting, which is, the down distribution, that's heavily shielded. Anyway, and there's probably other downlighting that's on the chairs and a million other things. So quite a nice bunch of combinations. Anyway, so when you do have any of these lighting techniques, or multiple ones, you'll really want to consider control of glare. Glare is kind of the enemy of good lighting design. The biggest reason, and I think probably some of you remember from the introductory class where I wore the headlamp, that having that headlamp in your eyes will adjust to that bright source, which basically means everything else gets darker. The slides got darker, the windows got darker, your screens all got darker because of that bright light. Turning it off or pointing it in another direction so it's not within your visual field. And if you look at this slide here, the normal line of sight is considered 0. This is this necklace person looking forward. At about 30 degrees, that is the angle at which bright light sources are going to be the most disruptive, up to about 30 degrees. What the chart is showing you is that you need a lot more light to kind of be irritating the higher the angle you get. So it doesn't take a whole lot of light to be irritating within your visual field, but as you get above it, it really, you can have a lot more light pumping down on the surfaces around you without it being an irritation. Now, different light sources have a different brightness profile. And just to show how a traditional incandescent lamp might have approximately 150 candelas, which is a measure of brightness. Candelas, if you think about it, it's sort of like a candle. So that's 150 candles squeezed into that little inch. This guy here, this is a typical fluorescent tube. And again, these are generic. It's clearly a lot less, 1/30th the surface brightness of the incandescent fixture. Now, there's a lot more surface, so you have different issues. But obviously, screening this so you don't see the super bright source in your visual field is very important. And different light sources and different fixtures will have ways to block that light. A baffle or a screen is a very common way. And what you'll try to do is figure out where is a person standing, or this bodiless eyeball, and you'll put a baffle, a solid opaque or semi-opaque object that prevents their line of sight from seeing the bare lamp. You can also increase the surface area. So if you take a lamp that's bright and you cover it with a giant globe or a lampshade, what you're effectively doing is increasing the size of the lamp, because now you might have 1,000-foot candles coming out off of this light source. if that 1,000-foot candles is divided only over this surface area, that's pretty bright. But if you expand the surface area with glass or fabric, that single bright light source becomes a lot less bright, even though it's emitting basically the same amount of light. And there's other things. There's diffusers, and you see these in elevators and that sort of thing all the time, where basically the light hits some surface, typically plexiglass or louvers, like egg crate louvers, and it spreads the light out and reduces the surface brightness. Even recessed fixtures, this is a parabolic downlight. Take this into account. You want to bury that light source deep in the fixture so that your line of sight does not actually see the bare lamp. Unfortunately, LED replacement lamps unfortunately, they're very notorious for being super bright because the LED source ends up showing up very close to the surface. I was going to take a picture in the corridor in the library, the kind of curving corridor in the back of the Halley Library. They replaced incandescent downlights with, they basically swapped out the reflector with a new one that's LED, and the LED light source is very bright, and it unfortunately does fall within your visual field. Kind of a rookie mistake. You guys won't make that mistake. You'll consider glare when you're doing your lighting design. And so many things, this looks like a pretty simple task here, right? Let's just light a desk. How hard could that be? And this is the most common thing, these fluorescent lights. The trick is that, well, first of all, you have to really know what surface people are working on. This person is reading, right? Well, what if they have a computer screen that's vertical? Boy, that's going to cause a lot more trouble. As opposed to somebody working on a tablet. A tablet is glass, and that's also very hard to restrict glare. So you'll have to really carefully draw out your designs and make sure that whatever lighting you put in, it takes into consideration the position of the furniture. Sometimes you don't know, and then you'll just want to use low glare fixtures, like the up-down or direct-indirect fixtures that we have in our classroom. And here's an example. You might have a grid of lighting in your ceiling, which is pretty common for open offices, a sort of general lighting strategy. Well, some of that light might be right above you, which is great in terms of glare within your visual field. However, if you have a heads-up task, which is kind of a way of basically saying you're not having your head resting on the tabletop, that's fine. If you have a task, however, where you're looking at a vertical surface that's glass, like a big computer screen, now you have a problem of that the computer screen is going to have brightness. So really you have to think about either things like offset dimming, which is where you offset which lights are on and off, having multiple circuits. So here's an instance of 2 circuits, and you could turn them on and off depending on the furniture arrangement. Also, having the direction of the light not be parallel to the computer monitor, if there is a computer monitor, is very important for glare. And along those lines, a little quiz, a little sort of mystery problem for you. See how observant you are. As you wander around campus or around the world in your life, and you go past people's offices from the outside, notice which direction they usually have their computer monitors faced. And you'll see something very similar to the problem we see here. So even things that seem innocuous, like paintings, if they are covered in glass, or they're a glossy surface on their own, the angle of the light source from that painting is going to be something you'll want to consider. Typically 30 degrees is kind of the magic angle for lighting paintings. Now, you don't always have great control over that. Track lighting may be fixed physically in the ceiling, and the size of the painting can vary, but that's kind of the magic angle. And even things like computer screens, a little bit of glare, a light source that's fairly bright, like a fluorescent light that is an exposed lamp, is going to produce some hot spots. They call these veiling reflections. because they kind of, it's like drawing a veil over your eyes, and it makes these these bright spots. Low glare fixtures will produce a lot less glare on these surfaces. And again, it depends on the position of the light source, the angle of the screen, the reflectivity of the screen, and all that. And we all know about how painful it can be to try and use your phones in the bright sunlight. You can even buy what are called polarizing filters to put on top of your glass screen that help it read, but of course that also cuts down on the light. So that is it for kind of brightness in lighting. Now let's talk about the color of light. And as I believe we mentioned earlier on, light is part of the electromagnetic spectrum. A very tiny portion of the electromagnetic spectrum is actually visible. And that spectrum can be divided up, and we're all probably familiar with like a prism and how it breaks it into the rainbow. And those colors of light, if you remember my discussion in class, that materials don't really have color. They have reflective properties. Those colors are just names that we give to wavelengths inside our little brains. So seeing red light is really a 600 angstrom wavelength of light. The red is just a name. We just name that part of the spectrum. But all materials, because they are solid, they're opaque, they reflect a different kind of profile of light. So if you have a yellow surface, you can shine red, yellow, green, and blue light on it, but only the yellow light will be reflected. And this is true for sunlight or any type of light source. Sunlight is an all-white source, which means it has all colors in it. So any color will look natural. Whereas if you had a light source that was just blue light, the blue light will only look blue when reflected off a blue surface. Green will not look green, it'll look gray. Yellow will not look yellow, it will look gray. And red will not look red, it will just look gray under that blue light. So that's why it's so important to have a light source that has what's called a full spectrum. It has a little bit of each color of light. And here's, I've always liked this chart from the book. I don't know why. I guess I like food. But that if you look at the reflective profile, so here's the spectrum of light, the sort of full visible spectrum. If you look at what colors lettuce, for example, reflects, what you'll see is that it reflects a little bit of blue, a little bit of lighter blue, and it reflects a fair amount of green and yellow. And then it doesn't nearly reflect as much red. It does reflect some, however. Tomato, obviously, is a different vegetable. It looks more red. It has a lot more red. It does not have zero in terms of the other colors. And that mixing is what gets the unique color of tomato. So in the physical world, you rarely see sort of single colors. Again, these are nanometers or angstroms is the old school word. And here's two materials that are lit using color light that is not full spectrum on the right and relatively full spectrum on the left. And you can see how the reflective properties of the material change the way it looks radically. And we've discussed in class how putting on makeup in bad lighting conditions or clothes under a black light, the reflective properties of those materials don't change, but if you don't have a full spectrum of light shining on those materials, they won't look normal. And just to kind of also remember here that solid materials that are finished materials or clothing or our bodies, those are typically mixtures of pigments, okay? So you add some cyan, magenta, and yellow, and you add them in even quantities, and you basically get black. Okay, that is the solid material, the property of the solid materials. When you look at the properties of the light that shines on it, it's reversed. You add those same three colors, and you get white. Okay, so they're additive primaries. all of this sort of background knowledge allows us to kind of score different light sources on how well they render colors. Okay, this is not a perfect science because every material reflects sort of slightly different wavelengths or combinations of wavelengths. And so a material that has more, a tomato might look better under one light source than another, even though lettuce might look better under a different light source. But it's a general scale. It's called color rendering index, CRI, and it's a scale of 1 to 100. Daylighting is the standard and equals 100. So a really good light source equals 100. Typically, incandescent light is considered 100 because it's very similar to daylighting in that you're burning something. You're just in the sun, which provides daylighting, of course. You're burning, I forget, hydrogen, I think, in the fusion process, and that releases light. In incandescent lighting, you're burning tungsten, or a candle where you're burning some other thing, oil or wood. So anyway, the big thing is, are colors perceived as natural? Okay, that's the operative word, if they are natural. So the way that these are scored, usually there's some kind of like panel that looks at the light, they measure the wavelength, and they create a chart with the spectral distribution of that particular light source, and they compare it to daylighting, but they also look at different materials. One of the things to consider is that as you change the amount of light in a space, that is going to change the way things look. So let's look at this spectral distribution chart. First, this is daylighting, and you can see there's basically a lot of light throughout the spectrum. It kind of tails off here in the violet colors. But this is natural light. This chart, spectral distribution chart, will change during the course of the day. You might have more red in the very early morning and evenings. And cloudiness will also decrease the red wavelengths. Now, if you compare that to something like a cool white fluorescent, you can see cool white fluorescent, and this just is a very particular lamp. Each lamp has a different distribution. You can see it's a pretty even curve. There's little funny squiggles and then these funny spikes that are very high in terms of light quantity in that particular wavelength. And what this means is that even though it's fairly similar in its distribution, a little less red than you'd expect, if you happen to be wearing a color that falls within this very narrow range, it's going to look super bright, much brighter than, say, one that's more of a mix of green and yellow. Fluorescents are just like that, and that's why we use them for black lights. Those black lights basically emit one very big spike right at the end here. So every color that you wear reflects different wavelengths. Most colors don't reflect any of that purple, ultraviolet, except when you're wearing white. And the reason that white looks so funny is because white shirts reflect all wavelengths, so they'll happen to reflect that very narrow range that shows up in the black light. Anyway, incandescent lighting, same thing, very smooth curve. You can see it's not the same as the natural daylight, but still pretty close, and there's no spikes, so you do tend to look more normal under incandescent lighting. And there are also cooler incandescent light sources. By cooler, well, we'll get to that in a minute, but things like halogen, which look whiter, and they tend to have a little bit more blue in their spectral distribution. And this is an example, not of just one LED light source. LEDs are relatively new technology, so it's actually kind of hard to find good spectral distribution charts for them as yet. Typically, LEDs, you can get a pretty full spectrum, and they've come up with ways to kind of flatten this curve out. So LEDs, the color rendering has gotten very good in recent memory. The big thing about LEDs is that the newer ones, you really have to look on the box. They will usually say their CRI, their color rendering index. Something like a fluorescent might have color rendering in the range of 75 to 80. Compact fluorescents are the same. And LEDs, they're in the mid to upper 80s in terms of their color rendering. The reason that they aren't perfect is that I believe that there are still little sort of divots in their chart, depending on the manufacturer and their techniques. And as I said, incandescent and things like candles are 100. Now, color temperature is another technical aspect of lighting. It is also a kind of somewhat subjective measurement. Not entirely. I mean, most of you, I think, can describe or at least picture the difference between daylighting at sunset over the ocean, where it's very red, and in the middle of when it's the middle of the day in the summer, where the sun is right above it's above your head, and it feels very almost bluish, that light source. These differences in color temperature are measured in degrees Kelvin. Kelvin is the absolute scale, related to the Celsius scale. And I've never quite understood this myself, but they use a black body radiator. And as you warm it up from absolute zero, it begins to glow. And if you think of like a campfire, sometimes the campfire is just kind of reddish, but sometimes it actually gets almost blue when it really heats up. Those are measured in degrees Kelvin. And here's a scale, handy dandy scale, just to give you a sense, like an overcast sky. It's kind of blue. And so that's going to be in this upper range, 6,000, 6,500. This one doesn't have LEDs on it. And one of the things about LEDs is because of the way they produce light, you can actually pick a color temperature for those. And some of them can even be adjusted on the fly, the fancier ones. But anyway, sunlight at midday, as a visual reference, is about 5,500 degrees Kelvin. Candlelight is probably some of the yellowest light that you can see, and that's about 2,000 degrees. Okay, so the typical range that we see is anywhere from 2,000 to 6,000, depending on the application. And one thing to be aware of, the color rendering, the higher the color rendering, the more natural materials look. The color temperature also has an effect on that. Color temperature doesn't really measure how well colors look, but the basic rule is with color temperature, the brighter the space, the more light you have in the space, that's measured here in foot candles, objects will appear more natural when you use a color temperature that's cooler. So if you think of something like Best Buy, Best Buy has a pretty high foot candle level in its floor displays. So the color temperature of those light sources is probably around 4,500 degrees Kelvin, just because objects don't look normal. Whereas if you're at a restaurant, the light level may be down around 15, 20 foot candles, which is in this range. For things to look normal, you're going to want to use a much warmer color light source. That's going to probably be incandescent or an LED with that warm light source. And you might say, well, why don't I just use what's cheapest or what's most efficient for showing off different materials? There are different illuminance targets. IESNA is the Illuminating Engineers Society of North America, and they publish recommended light levels for different conditions. And you know, this is probably pretty intuitive. Passageways tend to have a lower light level, recommended light level. A space where you need to read is going to have about 25 foot candles as the light level, so 10 times as much or more than a passageway. And then things like hobbies, which is kind of a weird way to describe it, but basically when you're making models and stuff, that's going to be even higher. And if you assemble machine parts in your house or something like that, do circuit board work, you're going to need even more than that. So when you say, oh, well, I'm going to need 50 foot candles, the color temperature of the light source you choose is going to want to be cooler, Whereas here in passageways, a warmer color temperature is fine because it will show materials in a more natural way. So that is basically it for the properties of lighting. The big thing here is when you consider the properties of the light in your projects, the biggest one is the direction of the light. Where is it coming from? Is it coming from the floor or the ceiling or from objects placed close to a task? And then the color temperature. The color temperature is generally related to the kind of recommended light level in a space. But there are other factors. For example, if you want something in the background to kind of fade off and you want to light faces, one might need a cooler color temperature, one might look better with a warmer one. And then finally, the reflective properties of the materials that you're using or you're trying to light. If it's a white wall, well, you have a fair amount of flexibility in that. But if it's, for example, clothing, you're going to want to make sure to have lighting that is really going to show off all the different textures and colors in the clothing.